Hello, everybody. So, so let's talk about inductors. So, as usual, for if you want to do circuit analysis with with a certain component, all you need to know about that component is the relationship between voltage and the current. Okay, so the exact relationship, if you want to derive the relationship, you want to look into the physics of that particular component. But as far as circuit analysis is concerned, which is the primary focus of this course, we only need to know the relationship between the voltage and the current. Okay, and that would be our starting point here, and we will take that as a given, and then we will start analyzing from there. So from physics, you can derive this. So let's say there is a inductor, and there's a voltage drop of V of t from left to right. Okay, and the current I of t is flowing from left to right. Okay, so that means this current is flowing in the direction of the voltage drop. Again, this is important. Okay, the current I of t is flowing in the direction of the voltage drop V of t. If that is the case, then the voltage and the current are related this way. Okay, where the voltage is proportional to the derivative of the current, and the proportionality constant is called the inductance, right? And it's measured in Henry. Okay, so V of t is L times the derivative of the current. That's the basic relationship. So if you're given I of t, then you can simply differentiate I of t and multiply by L to get the voltage. Okay, so that's first relationship, between the current voltage and the current. So now let's say if you're given the voltage and you want to find the current. Okay, so let's do some calculus then. Okay, so here I integrate on both sides of that equation. So and put the limits. I'm doing a definite integral, and the limits are from t0 to t1. Okay, and then I put the same limits on both sides. Okay, on the right hand side I have L times the derivative of the current times dt, right? So I can make a substitution here, and the substitution I'm making is U is equal to I of t. This means my du will be equal to the derivative I of t times dt, right? This is the standard way you do integration by substitution. So now if I make this substitution in the equation over there, my left hand side is still the same. Okay, and my right hand side, if you notice, this whole thing here is equal to du, right? And then that is what I have here, L times du. And I'm also making substitution as u equal to I of t, right? So that means on the limits, I go from I of t 0 to I of t 1. Okay, so that's my right hand side. And this is a pretty simple integral. And it's basically integral of 1, which is equal to u. And then I substitute the limits, and then I get this. Okay, I of t1 minus I of t0. So if I rearrange the terms here, then I get I of t1 is I of t0 plus this integral of voltage. Okay, and then please note that I'm labeling the equation so that I can use those use the equation numbers as a reference later. So now let's say if t of 0 is equal to 0, that means I'm starting at time 0, and the current at time 0 is equal to 0. Then if I substitute these values in the above equation, I get I of t1 is basically the integral from 0 to t1 of v of t multiplied by 1 over L. Okay, so now you know if you're given a voltage and you want to find the current, if you're given a voltage as a function of time across the inductor, and then you want to find the current as a function of time, then you can just integrate the voltage to get it. Okay, if the current at time t equal to 0 is not 0, then you have to use equation number 2. Otherwise, you can simply use equation number 3. Okay, so now we talked about the relationship between the voltage and the current. So given a current, we know how to find voltage, and given a voltage, we know how to find current. Okay, so now let's talk about power and energy. Now notice that in a resistor, let's say if you have a voltage V and the current I, okay, then V of t and I of t, let's say, and I of t is in the direction of the voltage drop, then the power dissipated, okay, will be equal to V of t times I of t. Okay, so in a resistor, this power dissipated will be dissipated as heat in the resistor, right? But in inductor, you won't see that happening. If the inductor is getting heated, that is because of not because of the inductance itself, but it's because of some other reasons. Okay, so in an ideal inductor, then the power is still IFT times VFT, where IFT is in the direction of the voltage drop, but this power being dissipated will be stored in the form of magnetic field. Okay, so when there's a current going through the inductor, there's a magnetic field around it, and this power which is dissipated will be stored in that magnetic field, right? So ideal inductors basically act like energy storage devices, and these are used very heavily in in many applications, especially coming to when it comes to DC to DC conversion, or or other power applications. These inductors are used actually pretty heavily over there, and they're used primarily as energy storages. Capacitors also perform similar things, but we'll look at that later. So anyway, so the power is voltage. Power at any given time is the voltage drop times the current in the direction of the voltage drop. Okay, so I can use any of the relationship between voltage and currents and substitute them and convert it into a single variable. So for example, I can express the current or express voltage in terms of current and get equation 5, or express current in terms of voltage and get equation this other equation here. Okay. But usually equation 5 will be very helpful because we don't want to deal with this messy integrals. Differentiation is easy, right? So if you're given a voltage, you can convert that into current, and then you just just use this equation. Okay, so equation 5 basically represents power at a given time in terms of the current at that particular time. Okay, all right, so now let's look at energy. Now I'm repeating equation 5 here. Now energy and power are related in this way, where power is basically the derivative of energy, right? That means the rate of change of energy stored is basically the power being dissipated in that inductor. Okay, so if this is how power and energy are related, then we can use the fundamental theorem of calculus to get this equation, right? That means if you integrate power from T0 to T1, that will be equal to E of T1 minus E of T0. Okay. All right, so let's label that equation 6 and keep it. I'm going to repeat equation 5 here again. The power is expressed in terms of current. Okay, now I'm going to integrate both sides from T0 to T1. Okay, and then the left hand side is just that integral over there, and the right hand side is I'm taking this and then integrating from T0 to T1, and I get this. Okay, again I make the same substitution here, u equal to IFT, and then du is equal to derivative of IFT times dt. Okay, and then make the substitutions. So T0 becomes IFT0 because you use IFT, and T1 here becomes IFT1 here. Okay, and then there's L, IFT is du, and then IFT dt is du. Okay, so now again this is a pretty simple integral. It's u du. So if you integrate that, it will become half u squared, and then I'm substituting the limits in there. Okay, and I'm going to use equation 5, the fundamental theorem of calculus, and then write the left hand side this integral in terms of energy like this. Okay, so E of T1 minus E of T0 left hand side will become half L times the difference of the squares of the currents. Okay, and then let's say if the current is 0 for all negative time, that means that there has not been any current flowing through the inductor. That means there's no energy stored in the inductor. That means and at time 0, the energy is 0. If the current is 0 for all t less than equal to 0. Okay, so what that means is, then if I substitute t equal to 0, then from this equation here, this E of T0 will become 0, and I squared of t, this should be T0, not T2. This should be T2 here too, T0 over there. Okay, so right, so I'm substituting T0 equal to 0. That means I squared of T0 is 0. So then the equation I get is E of T, energy of T1 is half L I squared. Okay, so there's a very simple relationship between energy and current. Energy is half Li squared, which we just derived, right? Now notice that in this equation here, the energy stored at time t1 only depends on the current at time t1 and nothing else, right? What that means is if we have two different currents, which took completely different paths to get to their particular point at t1, then the energy stored in the inductor at that time will be same in both cases, right? It only depends on the final value of the current. It doesn't depend on what path the current took to get to that point, right? That's what this equation means here. Okay, energy stored at any given time depends only on the current at that time. It doesn't depend on what the current was in the past. All right, and this is a very important relationship between energy and current for inductor. Okay, so to summarize, we did, okay, the relationship between voltage and current. If we know how to calculate voltage if current is given, and we know how to calculate current if voltage is given, and then we know how to calculate power. So power will be just this equation 5, right? And then we also know how to calculate energy stored in the inductor using equation 8. Okay, right, so we'll stop here.